MP3 is more sophisticated. Just for fun, we can also look at an og vorbis. People know what that is? That was invented at MIT by Monty. So here's the even more sophisticated one. So here he's adding noise even around the tones, but sort of smartly. So you can see here that noise falls off at a sort of curve. You see that? See how there's the big noise, and then it goes flat, and then it comes down? That's what og vorbis thinks is what we call the masking curve. Now, where do you think that came from? How did we figure out what the masking curve is? Any guesses? Okay, for MPEG, they got all kinds of people in a room in Geneva, and they did experiments on what tones they could hear and what they couldn't hear. For og vorbis, Monty sat by himself with headphones for years and measured what he couldn't hear. So it's very accurate for Monty. Okay, so that's how this MPEG compression works for audio. So the increasing sophistication has to do with deciding which, first of all, with finding the right transform here, the right filter bank, and then deciding which coefficients to give full precision and which not. That's how audio compression works. Okay? Okay, so I have one more demo. I'm going to run out of time here, but one more demo about what does MP2 actually sound like. Okay?
You're at 50 minutes now. So
how many now?
You have a little less than a half an hour left.
Okay. Okay. So here's, just for fun, here's what it actually sounds like. Let's go to. Okay, so this is one of my favorite pieces of music. People know what this is?
Oh no, Prokofiev, right? Rachmaninoff.
Actor of Truth. It's the Greek Piano Concerto #1.
Oh, okay.
Okay, so I love this symphony. Sorry, this concerto. And it has a lot of frequencies in it, so it's a good match. Okay? So let's just for fun, let's play an MP2 of it.
MP2, yes.
So this is a 32 kilobit per second MP2. How's that sound? Thinner, yeah, but it's pretty close. So the original was 700 kilobits per second, which is sort of a 32. So we're taking out, what, 19 out of every 20 bits, roughly. That's pretty good. Here's the original. Okay, and here's 32 kilobits. Oops. Taking out 95% of the bits. So where is the savings coming from? What do you guys think? We've divided into 32 subbands. How do we save information? Yeah, we leave out. We either don't send 8 bits per sample. We send fewer bits per sample on those vertical coefficients. By the subbands, I mean once we've got it all vertical, or we leave them out completely. So just for fun, let's play the bottom subband, okay? Just the 0th subband, okay? This is a feature that all MP3 players support if you dig hard. No, they don't. So subband equals 0. Okay, so here's a complete MP2 that has almost everything. This is what subband 0 is supposed to sound like. So that's, which coefficient is that of our vertical 8 coefficients? Which one are we looking at? That's just playing the top one, right? We set everything else to 0, we're just playing the top one. That's what you just heard.
That's the sum then.
Sorry?
That's the sum then.
Well, no, because it's a more complicated filter bank. This is 1/32nd of the whole frequency spectrum.
Okay.
Okay? So now let's hear what it sounds like when it's been compressed. Okay? So we're having less bits, but still just that first coefficient. Does this sound different? Sounds pretty close, right? Because that's where most of the information is at the lower frequencies. Just for fun, we can play the next subband up. So this is now the second coefficient we're letting have its value, and every other coefficient is 0. Okay, that's going to sound almost the same too. Those coefficients we're encoding with almost the same number of bits. The part where it starts to get dodgy is when we get a little higher, like subband 6. Okay, let's play that, and if any of you have sensitive hearing, I'll just play a small sample of it. Here's what subband 6 is supposed to sound like. You hear that? Okay, so this is where we cut out the bits. And to make it easier to hear, I've made it louder and I've slowed it down. So here's what it's really supposed to sound like. Okay, this is subband 6. This is the real thing. It's slowed down so you can hear it. Okay? That's what it's supposed to sound like. Here's what it sounds like after going through MPEG compression. Okay? Here's where you're really going to hear it. This is where we save the bits. And you didn't hear this when it was playing the whole thing, but if we isolate just subband number 6, here's what you're going to hear, the shocking truth. Okay, what's different? No, what was it doing there?
Was this what we saw the noise that you saw?
Yeah, well, yes, but this subband, if you listen to it, what happened to it that the real one didn't do? Yeah, it completely went away. It went to 0. The real one didn't ever go to 0. This one just completely was deleted. Did you hear that? Okay, so that's where we're saving the bits. You can hear that when all the subbands are playing together, but if we isolate just that coefficient, you can really hear it. Just cuts it out. So that's how MPEG audio saves bits. That's what it sounds like. It's just you're missing some of the subbands some of the time, or they're being quantized with big jumps. Okay, that's all I have time to say for on that. Any questions on that before we move on? Yes?
How do you decide when to cut off which band?
Well, you need to have that masking curve that tells you what you can hear and what you can't hear. If the masking curve says, that they don't think you can hear it at all, you might as well just set it all to 0.
And you just write a program that decides when to cut which band?
That's the encoder, yeah. The decoder is much easier. You just play what they gave you. But the encoder, Monty's got to sit with headphones for 2 years and decide when he can hear it and when he can't. Yes?
Why is it easy to pick one to delete when they have the column representation?
Well, what is the row representation? That's like the amplitude of the whole music at any point in time. So if we set any one of those to 0, the whole concerto would go to silence. So we can't do that. You're going to notice that. But whereas you're not going to notice if one of the frequency bands gets set to silence because it's been masked. So we had to transform to a basis that's appropriate for the masking effect. So that the choice of basis is $1 billion question. His accent is changing.
So what are the 0, 1st, 2nd, 3rd, 6th, etc. subbands mean? What does it mean every time, roughly, that you increase the number?
Well, I said there were 32 bands, right?
Right. So what do they roughly correspond
so roughly, if it's the first subband is roughly from 0 to 700 hertz.
Ah.
And the second subband is roughly from 700 to 1400 hertz.
Okay. So these high pass and low pass filters you're doing are essentially a version of a Fourier transform.
Yeah, essentially. So the first step of this filter bank divides the whole frequency band from 0 to 10 kilohertz and then 10 to 20.
Okay.
And then we run it. The next one goes from 0 to 5K and 5K to 10 and then 10K to 15, 15 to 20. So it's again, it's a sort of recursive filter bank. Okay? Great. Let's move on. Okay, so let's talk about video. Okay, we talked about audio. Now we're going to talk about video. Oh boy. Okay, we're going to rush through this. Okay. So we're going to talk about video. Video is very complicated. It's not like audio where you just can plug a microphone into a computer and get a bunch of voltages over time that are the amplitude. Okay, video is more complicated. Let's talk about it quickly. If you look at a nice scene, what are you seeing? What's coming in? What are you perceiving? Light. Okay, good. Electromagnetic waves, and when they come in, what do they look like? When a wave comes to a particular spot on your eye, how do we represent it? Well, there's rods and cones before that. Before that, how do we represent a color of light?
Oscillating electric field.
Yeah, an oscillating electric field. Good. And what's one way to decompose that?
By their wavelength.
By what?
Wavelength?
By wavelength. Yeah, but when you look at a color, is that just one wavelength? It does depend. But so how do we describe electromagnetic waves in 802?
Polarization.
Yeah, okay, forget that. So there's a whole spectrum, right? There's a whole spectrum. You can have light of a short wavelength, and you can have light of a long wavelength. And the light that comes in has different magnitude depending on the wavelength. We perceive from, let's say, about 340 nanometers to, let's say, 360 nanometers to about 740 nanometers. So there's a whole spectrum, okay? And in real life, not only is there a magnitude, but what is there when you do this frequency decomposition? Yeah, well, not only is there an amplitude, but if it's a complex amplitude, that means we have a magnitude and a phase. Yeah, so we'll forget the phase, we'll forget polarization. We're already simplifying the problem. We just have different magnitude across the frequency spectrum, okay? So let's say we've got someone with a very interesting color that we want to reproduce on this screen, okay? So let's start off. Who's got the most interesting color here? I kind of like you, sir, with the shirt. Yeah, you.